In the next unit, we'll look at some more advanced ideas for still parameterized algorithms, both upper bounds and lower bounds, things that deserve a bit more context. And so I took them out of the other two units. Conceptually, they belong in the previous two units, which were about algorithms with parameterized techniques or lower bounds. But these felt they're distinctively more involved and built on some extra steps. So I split them off to have the space to devote a bit more time to the setup. And hopefully the techniques go well beyond these specific examples. What we'll start with today is a bit of a detour first on linear programs and linear optimization. And then we'll apply LPs. The first application we'll see will be for a better kernel for the vertex cover problem. And there's a short section at the end also on some advanced lower bounding techniques. So far, we've really had this dichotomy. Either there is some FPT algorithm with an arbitrarily bad function, potentially, f of k. F could be a really fast-growing function. Or it's W1 hard and we don't expect any kind of FPT algorithm. But for problems where we do have an FPT algorithm, we might want to know if we can say something about this function f of k. A specific algorithm always gives you a specific function, and that may or may not be a good one. It'll be super polynomial, but maybe it's not clear how far you can push it down. And there we'll see some techniques with stronger assumptions, giving you some lower bounds that go beyond saying there's no FPT algorithm whatsoever. That's the plan. Let's start a bit with the practical side of linear programs first. And so I pitched this really for people who've never seen it. If you've seen it, maybe the first part is easygoing. What are linear programs? First of all, the name, I guess, is just showing the age of the technique. It's from just after World War II. And a program at that point didn't mean a computer program, really. There were no such things in widespread use. Instead, it's more the planning, or a program was a schedule, rather. So think of it that way. It was motivated from the application to call it like that. It's a bit like dynamic programming, same kind of era. So what are they? The name is just what it is. I guess it's here to stay. It's a class of optimization problems. And unlike most of the things that we deal with in this module and most of computer science, it is about continuous optimization, not discrete or combinatorial. It does have a combinatorial flavor to it, but we'll come back to that. So it's always something you want to minimize or maximize. That's what optimize means. And there's some side conditions that constrain you in doing that. Now, the interesting bit about linear programs is that they can be solved exactly in polynomial time in a completely clean sense. So I didn't define the formal problem to say in P we would have to say what the decision problem is. And then really the decision problem is a bit less exciting maybe, because it's really just talking about linear inequalities. But yeah, so the appeal of linear programs comes from the fact that we know solvers that can solve them worst case polynomial time. And they can also be solved in practice for really large instances. I mean, one reason is that it's a polynomial time algorithm, but also because of its widespread use, people have tweaked these algorithms and made them really clever. So it goes far beyond saying there's some polynomial time solution. It's a bit like SAT solvers, which are often fast in practice, but here the difference is also in theory, these solvers are clearly polynomial. Okay. The specific names are maybe not so important. If you've seen LPs before, you've probably seen the simplex algorithm. And maybe know that that one's not polynomial in the worst case, but there's other methods that are. Let's introduce what this is about with a little whimsical example. So suppose you're an apple farmer, and you're trying to maximize your profit, but of course there are constraints of real life that stop you from just earning infinite money. I guess the way to earn infinite money is to have as many trees as you can think of, and also sell your apples at infinite prices, which for various reasons won't work. So the real thing is modeled here like this. So you're devoted to promote the varieties that have grown in the area for long and have picked. So these are like the last 2 years of Hesse's specialized apple varieties that they picked as some historically relevant varieties. Doesn't matter so much. They're just two names, Sossenheimer Rote and Korpacher Edelrennet. Two types of apples, and that's all you're gonna do. You plant trees of type S or of type K, if you prefer. Now they have different yields, and also the apples yield different prices. So here we're just saying per year, one tree of each variety gives you a certain amount of money at the end from selling the apples. As he has an orchard of a certain size, and each tree needs a certain amount of space. And also they need fertilizer and time to harvest, okay? These are the main constraints. We have space constraint. We need to put fertilizer to get the trees growing, and they have different requirements there, just because this is a bit more sturdy one, and the other is a bit more needy. And then the harvest, I don't know how to justify the 3 times increase. It made the numbers work out nice. Suppose this is basically, what can we make up? So these you have to pick at the exactly right time, and for the others, it doesn't make such a big difference. You can pick them and they ripen after you've picked them. Now, the other assumption is that Hesse really has a tight budget and can only afford a certain amount of fertilizer per year, and can only hire people to do the harvesting for a certain amount of hours per year. And these are hard constraints at this point. So that's the setup. Okay. Yep. Question?
Everything in this problem must be linear in relationship to other things. Yes.
For linear programs, the question was if everything has to be linear. For linear programs, everything has to be linear. The way it's defined here, it actually is linear, because the amount of space per tree is a constant. The amount of fertilizer and time per tree is a constant, and the amount of money you get out is a constant. As often, this makes sense to a certain degree. I think it's fine that here things are proportional to the number of trees for a while. Now, clearly, nothing in real life is ever linear forever. Like if you were starting to plant 1 trillion trees, you'd certainly not receive the same price per apple than if you have a normal amount that doesn't just flood the entire world with apples. And similar, I guess for the other things, there's kind of limits where it starts to fall apart. But within reasonable constraints, I mean, we're constrained here anyway, so we won't grow 1 trillion trees. Locally, it often is a reasonably close approximation to reality to have this linearity assumption. And so it's the very critique that the inventor of linear program, George Danzig, got in when he presented to the math audience back in at that time his algorithm to solve those. And they also objected, yeah, the world is not linear, right? But it seems locally it often is sufficiently linear that it gives reasonable results. And LPs are used in logistics and planning and scheduling a lot, where this seems to be good enough. But it's, of course, a legitimate question. Here it's essentially, you can say it's a modeling assumption. So the question is, how many trees of each variety should we plant to maximize the profit? And maybe also interesting, if you think of it from a economic perspective, we're constrained by various things here. Which is the tight ones? Are we? Well, maybe you can try to make a guess. Like the result will be something. Maybe you can guess how much money can he make in a year from this orchard if he picks the best combination of trees. And what's the actual constraint that hurts us, that stops us from earning more? Do we run out of space or fertilizer or harvest hours or some combination? Time? You harvest hours? Okay. And any guesses for the overall profit? You can do some quick, like, so we're gonna have from the space, I guess, less than 1,000 trees and so on and so forth. You can do some quick bounds, right? It can't be more than 1,000 times this. So 250,000 seems like a very optimistic upper bound. It's probably going to be lower if you look at some of the other constraints. Now, this is a simple problem. Just there's two variables, right? The number of trees I grow of type S and the number of trees of type K. And the numbers are small, is all relatively easy to figure out manually. So in this case, you can work it out. In general, maybe you see already that this is helpful to have a computer help. So this problem is a classic operations research question. And you can write it down as an LP formally like this. We're trying to maximize the profit, which is 195, or maybe you have to go back once in a while for the numbers. 195 for each type S tree and 255 for each type K tree. So I'm just picking two variables, S and K, for the number of trees of type S and the number of trees of type K. And then we have some constraints. The easiest are maybe the last ones. We can't build negative trees. Why would that ever make sense? Yeah, you know, optimization problems sometimes do funny things. If you say you run out of harvest hours, the result could be that you do negative trees of one type to create time for harvesting from the other trees, which mathematically might work, but of course doesn't make any sense. So these are constraints that we need for that purpose. And the other three are just reading off from the slide. The total space is bounded by 4 times the total number of trees. And then for the fertilizer and harvest hours, you get these two. Okay? So far, so good, right? Okay, some terminology to bring this back to land of math and linear optimization. We call this thing the objective function. That's the thing we try to minimize or maximize. The direction of optimization is called the optimization goal. Well, we'll come back to all of these. And one of those inequalities is called the constraint. And we give the whole thing a name just to be able to talk about it more efficiently. Okay, what else? The variables, I forgot about those. I mentioned S and K, the number of trees. The implicit assumption is that these are always real numbers. Now, some combination, some values for the variables here in some is effectively a point in R2 is called a feasible solution if it satisfies all the constraints. You can pick arbitrary numbers, and that's always a value for the variables, but not all values for variables satisfy the constraints, of course. Then the largest possible value, or the best possible value in general for the objective function, is the optimal value. And we'll abbreviate that with set star, just have a short notation. And an optimal feasible solution, so a solution that's feasible and achieves the optimal objective value, is called an optimal solution. And we'll also denote this by the variables with a star. Now, this need not be unique in general, right? There could be many ways to pick the parameters, the variables, to maximize the objective, but any of these will be called an optimal solution. Okay, names clear? So apart from manually messing with the problem, and in this case, that's good enough to figure out the optimal solution, we can also do a very systematic approach that will effectively lead to the simplex algorithm. Because it's in 2D with two variables, it's easy to draw. And so just to go over this quickly, we have a constraint for the space, which means I really should have put, so this is pointing this way, right? We're below this. Below this line are all the points that satisfy this constraint. So we've cut off this part of the region. No point up here can ever be useful. But all the points down here so far are fine. Now we can add one constraint after the other. For example, the harvest constraint is this blue line. So everything below the blue line is fine with that constraint. And if you take the two together, you get this region below the two lines, below the minimum of the two. So far, I guess I'm getting new lines each time. So that's the feasibility region so far. Now it's this region. Now we have a third constraint, right? The fertilizer. Aha, now you see actually the region is shrunk to this, and the space constraint is never really relevant. It's entirely outside of this area. So only points in this lower part can ever be feasible. What's missing is the non-negativity constraints. So the actual feasibility region is this purple shape here. In general, you can already see here, it's always going to look in 2D like a convex polygon. So a thing you get as the intersection of half spaces. So you take a line and everything to one side of the line. If you intersect an arbitrary number of those, you'll always get a convex polygon where all the corners, where all the vertices are on the convex hull of the thing. I don't know if that helps you. Okay, but that's not all. So we know all the purple points are feasible. They satisfy all constraints. How do we find the optimal one? And the graphical way to do that is to plot the objective function. And the objective function, you can say, I'm fixing all values for x and k, for s and k, that give me a fixed certain profit, say 50,000 euros. And they all lie on this line because the objective function, again, is also just a linear number. If you set that equal to 50,000, you get a certain line. And that's the one that's drawn here. Now, it looks like that's not the best you can do. You can plug in different values for the revenue, and you get a different line. And you see that with larger numbers, it just moves up and down. It stays in the same slope. Just the intercept at the y-axis is different. And you can keep pushing that line up until you start to leave the feasibility region. And so at this value, 155,500 euros is the point where you exactly cut this corner. And at that point, you have to stop. If you increase it one further, then you're outside of the purple. You don't cut the purple region anymore. Okay? Good. So that's the optimal point. And you could read off, you try to read off from the graph what the solution is, but of course you can just solve the equations. So what else can we learn from this? I mean, first of all, the solution tells us to plant 100 trees of type S, fine, and 533 and a third types, trees of the other type. That already hints at one problem. The solution could tell you things that might not make sense because it's continuous. But let's suppose this is not a problem in our case. We just give up one tree. And indeed, both the harvesting time and the fertilizer are tight at this point because we're lying on the green and blue line. So both of these constraints are maxed out. We could not have more trees for two reasons, if you want. whereas the space is never a problem. In this case, it's boring because it lies completely outside. It could also have a line here where it would sometimes make a difference. But if you're Hesse, you know what to change now. You need to somehow get more fertilizer and more hours for harvest. Whereas you don't need to buy new land. Maybe that's a good thing. Okay. Questions up to this point? Yeah. It's given in depends what your task is. In this case, it's given, right? This function is the objective. I could have used the colors here. That was the objective function. Now, all that gives you is the slope of this orange line. And what it doesn't tell you up front is where to put it, in how high to put it. That's the task of solving the LP. But we'll see like this systematic ways to get there. I just wanted to make one point, namely that this is very easy to do in practice if you need to. So here's a little Google Colab with code to solve this specific problem. The setup is essentially taken from Google's OR tools, which makes this very, very easy to do. And that's all you need. So you define, well, you need to import some solver code and so on, but this is, as I said, I just took this from their documentation. The real problem starts here. You tell it the variables, S and K, and you can give them a range. So here, that's encoding the non-negativity constraints. It's between 0 and infinity, plus infinity for both variables. Then you put in the constraints. And by the magic of Python, you can actually give these as expressions and it'll take them apart again. It's a pretty concise notation. These are literally the constraints we had on the slide, just typed up in Python. And you tell it what to maximize or minimize, and you say solve. And there's some boilerplate code to get the result, and then it spits out the answer. Okay. So if you ever need to solve an LP, don't try to invent your new algorithm. It's really not needed. And the thing is, as you know, 2025, if you know that there's libraries that do it that well, you can ask any AI assistant to write the code for you, so you don't even have to look up that part. I did it old school and copied it from the documentation, but the documentation also has another fun problem. Stiegler's diet, which is just the story is a bit fun behind it. The idea was this is a person that came up with this problem before linear programming was invented. And so he originally solved it with some manual tweaks, but not optimally. And now it's kind of a standard thing. The setup was, how can you meet your nutritional needs with spending the least amount of money? And so he took what was known at the time, and this is 1940s. So people cared about calories and protein, not about fiber. And I guess calories kind of subsumes carbs, but it's not a specific, like it's not an extra item here. And a small selection of vitamins and minerals. And then he put in all the standard food items they could find and what they give you in terms of the nutritional value, plus a standard price in terms of, well, US dollars in the 1940s. So the numbers that will come out will look really ridiculously small, but take into account that there's a bit of inflation going on since then. I guess 40s to now is 80 years, so it should have doubled 4 times or so. doubling every 20 years. Yeah, roundabout. Pardon?
Which column is the first?
Good question. So 1939 prices in cents is the third column. So this one, okay, 10 pounds of wheat flour cost 44 cents. Wow. And you can do the same. So you can set up the solver and automatically add the constraints without typing them up another time and let this thing solve. So if you do that, just because it makes one point I wanted to come to, it shows you what you should do. First of all, the annual food price is $40. Even if you take that times 4 or whatever inflation makes of it, that's not much, right? Now the catch is, what should you eat? A good amount of wheat flour, beef liver a bit, cabbage, spinach, and lots of dried navy beans. Yeah. So if you apply linear programming to the real world, it'll ruthlessly maximize the objective and stay within the constraints, but nothing else, right? And it also means you take all the slack out of a system, which sometimes, if you look at train timetables, etc., sometimes you get the feeling that there was one optimization function or one objective at the expense of some others. So that's always to be taken into account. The LP only tells you the solution in your formal model of what you put in. I guess the other point to say is, even if your problem is a tiny bit bigger, like in this case, has around 100 variables, it basically solves it instantly. You don't see anything. Okay, what's the general LP problem, apart from these concrete examples? In general, you'll have a bunch of variables, say n variables, x1 to xn. They're all real numbers. They may or may not be constrained to be non-positive, non-negative. I'll sometimes write this less and greater sign as just as a way to say there's nothing to see here. It's not a constraint of any sort. It just is an explicit way to write that there's no constraint for xj. And you can have actually 3 types of linear constraints. You can have some coefficients times each of the variables equal to some right-hand side that ties the values to some specific, or ties the values somehow down exactly. You can also have lesser equal or greater equal constraints. That's up for you, whatever makes it more natural to model the problem. And of course, here it's brought in the nice shape that all the variables are on one side and this constant is on the other side. Of course, you can, it's equations, linear inequalities, you can move things around. In general, if you write down such a problem, what can happen is one of 3 things. It can have a finite, clearly well-defined optimal value, like our examples. It could also happen that your constraints are actually contradictory and you don't get any feasible point at all. If you're not careful, this could happen. Then we call the problem infeasible, because there's not even a single point to pick, let alone an optimal one. And the other option is it could be unbounded. If somehow the constraints don't constrain you that much, you could make, like in this case for minimization, you could make the objective arbitrarily small, minus infinity. Then the problem is called unbounded. So that's one additional thing to take into account. For algorithms, they have to detect which of the 3 cases happens. And only in the first one, it makes sense to compute an optimal solution. As it turns out, all the algorithms for LPs can do that. And in polynomial worst case time, they can tell you which of the cases applies. And if it's case A, they can spit out the optimal solution, or a optimal solution. Okay. Let's see one more algorithmic example of what we can use LPs for. And this is maybe the oldest thing modeled as an LP. It's the max flow problem in graphs. So if you haven't seen this, the problem is given a graph with some vertices singled out S and T. And this in general is a directed graph, so it could be whatever, arbitrary. And think of these as directed pipes or streets with a certain capacity. So the capacities are just telling you how much flow you can send across an edge. I'm not going to write these down. The question is, how much flow can you get out of S and into T? Constrained by how much you can put on each of these edges in between, and the fact that you cannot lose objects in the middle or cannot use fluid in the middle. If there's 5 units coming in through here, 5 through here, and 10 through here, you should have 20 going out. Only in S and T there can be an imbalance. That's the max flow problem. The goal is to maximize what you can route from S to T, but that's actually the same as what leaves S, right? So we call that capital F. And then we have some capacity constraint on each edge. If you write that as an LP, it's a very naturally fitting in this shape. We maximize this flow value. The flow value is actually what flows out of S. So you can write that formally as, I guess I should say what the little f is. That's a variable for the edges. Each edge has an amount of flow that you can send across it. It's some real number. It's got to be non-negative because we don't allow negative flow in this case. And it should be bounded by the capacity of the edge. So f of the edge, I'm writing VW for the edge V going from V to W. So sometimes you would write it like this, or you would write it as an ordered pair. I'm using the more space economic version here. So the total flow you can write as everything that goes from S to some other vertex minus everything that comes back, because you could have edges leading back to S. And the other constraint, the not so trivial one maybe, is this flow conservation constraint. You have this for every vertex. That's what I said before. If it's not S or T, what goes in has to go out. And so this is what goes in, everything that comes from some vertex W and goes into V. And that has to be the same as what goes out of V into some W, summing over all the other vertices. And here these sums, it's a bit of a shorthand. You should interpret these sums. If there is no edge, then there is no summand for that vertex. So that's very, very well, essentially fitting exactly the form of LPs that we had. And so in undergrad algorithms, classes usually develop some tailor-made algorithms for the max flow problem. And indeed, you can, in general, solve this a bit faster than general LPs. But you could also take your network, encode it as a linear program, and let the LP solver do the rest of the work.